Hi, also a slightly different location for our video this week because I'm actually in my office. I tend not to record from my office, I tend to record from home because people knock on my door quite often, so we'll see if we actually manage this in one take without people knocking on the door. I'm here today to talk to you about design patterns. You may have heard some things about design patterns in the object-oriented analysis and design course that you did last year. And you may also remember that we talked about design patterns a bit today in our quiz. So we talked then about the state design pattern, which the book talked a bit about using for AI. And we talked about the singleton design pattern, which is using one of the examples in the book. So as a reminder, the role of design patterns is it's a way of defining the class structure in a program design. So you're used to doing class diagrams, things like UML. Design patterns are a way of allowing you to structure these classes and maybe structure your class diagram. Our aim, which is always good in good object-oriented design, is to maximise cohesion and minimise coupling. And if you don't remember what cohesion and coupling mean, look back at the video a couple of weeks ago where we talked about the event-driven programming, and you'll see an overview of that back then. We're also, as much as possible, trying to avoid code duplication, because code duplication is also a bad thing to have. So I'm going to go through a case study and look at how a design pattern can be used in that case. I am deliberately not using a game. Okay, so I'll be talking about an ATM, and I'm sorry if this brings back horrible memories of doing an ATM practical a few years ago, but I'm doing this because I don't want to accidentally show one person how to do MVC for their game. It would be unfair, it'd give them an unfair advantage if I talked about their game type. The code looked quite similar to their own, and they knew the answers from that. So I'm using an ATM as something that's completely different from a game. So let's look at our ATM initial requirements. So the ATM provides access only to one account to begin with. The account should have an account number and a balance, which is the amount of money left remaining in the account. The balance of the account may be viewed, so you can say in the ATM how much money have I got left. You should be able to take money out of your request, out of your account, but you should only be able to take money out of the account if there is enough money there that the balance left will be sufficient. We're assuming that we don't have any overdrafts here, so we're making sure that we've got enough money in our account to provide the balance. So here is our basic class diagram for that. You've got the ATM form, which is the main GUI that displays this on the screen, and you've got the account information that goes into that ATM. So far, all very simple. Let's just evaluate that design. Will this work? Well, for this level program, that design's probably okay. One of the key principles in using patterns actually is to avoid needless complexity. So you don't really use a pattern unless it will help you, unless it actually gives you something that you wouldn't have otherwise. However, our initial specification needs to be extended. The ATM that accesses only one account for one person, sort of a one-person ATM, personal ATM if you were, is really not very practical. In reality, ATMs tend to access lots of accounts. So our first amendment to our requirements then is that an ATM can access lots of accounts. How do we change the design to add that feature? Well, what we could do is just store a list or array of account objects in ATM form. This would look like this. So the 1 star means that ATM form contains any number greater than or equal to 1 of accounts. So it's now a one-to-many relationship. Okay, so far so good. But again, we've got to stop and think. Where is that account data stored? It may be a database. It may be an XML file. Perhaps it's a web service. Perhaps it's actually different for different banks, and our ATM has to access different banks and different sets of accounts. So we'd really like flexibility in terms of that data access, which means it's a really bad idea to hard-code the accounts into the ATM form class. So you have to think about that link between the display and the data. The form displays only one account's data at a time, so there's no need to load lots of accounts into the form. We only need to see the one that we're currently using, i.e. the account of the user who's put their card into the machine. The form doesn't need to know the actual structure of the accounts. They don't need to know if it's a database or an array or how it's stored behind. They just need the information as and when they need it. It is only an interface to display and enter data. So we can make our code far more flexible and allow us to work with different banks and different use cases if we decouple the form from the account data. And this is where the model view controller design pattern really comes into account. It is really the central pattern for all GUI programs, and this includes games. There's another one, which is the Entity Component System, which has some resemblance to MVC, which is also used in games. But the MVC is the main one, I would say, for GUI programs, and probably actually still the main one for games. The idea in this is to separate the visual interface, which we call the view, from the non-visual data and calculations, which we call the model. And the view and model are linked by the controller, which is usually the event handlers. So if we go back to our class diagram for ATM, the view is the GUI for the program. It should handle only display related things. Okay. Then we've got the model, which should handle all the data management, the calculations, anything that's non-visual, anything that's going on behind the scenes. The model should not have any direct access to the GUI controls. What the model does have is access to a list of accounts. The data stored for the accounts can be changed without affecting the view in the slightest. So if I decide to upgrade my bank from an SQL database to a NoSQL database, I can do that, and I don't have to change my view or the way my ATM works at all. The controller links the view and the model. Typically, it consists of the event handlers for the controls in the view. To summarise, so the model part of the MVC represents the business logic. It's what the calculations that are going on behind the scenes. It's the management of the data. It's data structures that represent non-visual aspects. It should be completely independent of the view. The view manages the user interface. It displays the controls, it displays the data, graphics, tables, and so forth. In a game, the view would also give force feedback to controller and so forth. So anything that comes as part of that user interface. It's common to have several views for one model. For example, think of PowerPoint. You've got the editor, the slide sorter, the slideshow, and they all refer to the same set of slides. In games, you can have the same game run on mobile and tablet and PC, and all you would have to edit there would be the view. You wouldn't have to worry about the model of the game behind the scenes. The controller manages the link between the view and the model. It's most useful when different types of link are possible. So things like web applications is the place we often see MVC. You can use standard web services like ASP.NET, GSP, so forth. That's absolutely fine. For standalone apps, sometimes the controller is merged with the view. If you look at Visual Studio's event handler code, it actually does merge the view and the controller. So here is the overview of the MVC pattern. You can see the model, which was our business logic, the view, which actually gives the input and output, and this controller sat in between, making sure that these things are quite separate, which means that in your game, if you suddenly decide, right, I need to change the graphics, then that should be quite easy because you just change the view part. Or if you decide that actually this is getting quite complex in regards to having too many images on the screen or something, and you need to change the data structure they're stored in, again, that's be quite straightforward, just change it in the model. So it gives you that separation that gives you a lot more flexibility in the design of your game. MVC is a high-level pattern. What does that mean? It means it's used to organise a large-scale program. So it's not just about one class, it's about looking across lots of class. In fact, and you'll see this when you do the reading this week, every component can be built from other patterns. Model view separation is really important. It's in fact it's the basis of all GUI programs. The controller is often integrated into the view, and it's done so, for example, in Visual Studio. For more information, you are going to read Chapter 12 of the Head First Design Patterns, which will cover MVC in a lot more detail. The value of MVC is it separates the model from the view. Oops, sorry, one slide too far. It separates the model from the view, allowing different teams to work on each component. The view is often designed by a graphics specialist. The model is often designed by a technical team. And so this means if you're working across a big team of people, you say, okay, you're doing the view class, you're doing the model, and they only need to talk about the interface between the view, the controller, and the model. And so it makes working in teams on big graphic problems such as games a lot easier. Okay. I'm actually going to stop this overview of the MVC design pattern in particular, which is really just there to give you an example of a large design pattern and why it could be really, really useful. And I'm going to make a separate video about design patterns in games in a few minutes.